Looks like we might be live. Alrighty. Hello everyone, welcome to the Math2521/2621 seminar. My name is Fred and I'll be taking you through the first part. Okay. So my part will be including the intro to complex analysis and limits and differentiability. Okay, so a bit of some basic rules. This is just from Math 1a. So firstly, a complex number is a number that can be written in z equals x plus iy, the Cartesian form, or z equals r e to the power I theta, and that's your Euler form. So one form's using your x and y coordinates, whereas the other form uses your modulus and argument. Okay. So normal rules of addition, multiplication, subtraction, and division, they all carry over from the real numbers. And with division, the trick is to multiply the top and bottom by the conjugate of the bottom. Okay? And geometrically, multiplying complex numbers just involves just rotating the complex number and a scalar factor. Okay, just a couple of important ideas. The mod of z squared equals z times its conjugate. This one's really useful in proving some proofs, such as the triangle inequality. And the principal argument denoted with the capital A, it's just the argument such that it's between minus pi and pi. Okay. So, firstly, we have the triangle inequality, and it states that the mod of w plus z is less than or equal to the mod of w plus the mod of z. Okay, just a quick geometric intuition. So say this is w, this complex number is z, and this complex number is w plus z. And if we want to have a look at the lengths of the complex numbers, we just take the modulus. And we know that the sum of the two sides of a triangle is bigger than or equal to the length of the third, and hence that's what we get this triangle inequality from. Okay. And the circle inequality states that the mod of w minus the mod of z is less than or equal to the mod of w minus z. Okay. And a quick intuition behind this is if we consider two circles, so let's draw up our axes. So let's say we have circle 1 over here and circle 2 over here. So let's say this is the complex number w, and let's say this is the complex number z. Okay, so that means this complex number, this vector here, is going to be z minus w. Okay, and if we have a look at the length, so we take the modulus, that's going to represent the radius of the inner circle. If we take the modulus of z minus w, that's going to represent the length of this vector here. So, and since this this length here is also going to be the mod of w, okay, that means this tiny length here, that's going to be mod of z minus the mod of w taken the modulus on both sides. Okay. And if you have a look at this, this blue line here, that's always going to be less than or equal to any red line. So let's use red. Any line over here. And that's essentially where we get the circle inequality from. Okay. Next part is we're looking at topology and sets. And first of all, let's define what a bore is. So an open bore with a center z0, center z0 and radius epsilon, written as b z0 comma epsilon, and that just represents the set mod of z minus z0 is less than epsilon. Okay, so that essentially just looks something like, whoopsies. That just looks something like if we have Cartesian plane, the point z0 is over here. Okay, and we have should be dotted. Okay, there we go. And that's just representing everything inside this circle. Okay. Alrighty. Now we have essentially three types of points. Okay. The first one. So firstly, let's consider a set being a subset of the complex set. Then the element x. It must be one of the following 3 points. Okay. Firstly is the interior point, and that's essentially when we can find a bore surrounding that point such that the entire bore is inside the set. Okay. So just one quick example. If we have, let's just consider general set. Okay, so let's consider this set. So let's say we have this point over here. Well, clearly we can find a bore such that the entire bore lies inside the set. Okay. For the exterior point, that's sort of the opposite. Essentially, we can find a bore such that the entire bore lies outside the set. Okay. So let's consider this point over here. Clearly, again, we can find another bore around the point, and notice that this entire bore lies outside the set. Okay, and the boundary point is when none of condition 1 or condition 2 is true. So essentially, let's have a look at a boundary point over here. And essentially, no matter how small you make the bore, there's always going to be part of the bore that lies inside the set and part of the bore that lies outside the set. And that's what we call a boundary point. Okay. Now, we have a bit of some types of sets. So again, let's consider a set S being the subset of the complex numbers. Condition 1, the set is open if every point inside the set is an interior point. So just a classic example. The bore, center 0, radius 1, that's going to be an open set. Number 2, a set is going to be closed if the set contains all of its boundary points. Okay, so if I were to instead highlight the boundaries here, this open set of the bore contains all of its boundary points, and hence it's going to be closed. Okay. The closure of a set, again, is just the set plus all of its boundaries, as we did in the previous case. And number 4, a set is going to be bounded if we can fit the entire set inside another bigger bore. So notice this set here, we can fit it inside a bigger bore, and hence it's going to be bounded. It's compact if it's closed and bounded. Okay. And number 6 is your region. So A region is essentially an open set with none, some, or all of its boundary points. Okay. Now this definition might be a little weird, but it's essentially to exclude, let's say we have a line. Okay. A line, we can't represent that as an open set plus some, none, or all of its boundary points. And the second case we want to exclude is just points. Okay. Again, a point, you can't represent it as an open set with some, none, or all of its boundary points, and hence is not a region. Okay. But some classic examples is again, if we consider the ball, center origin, radius 1, this is going to be a region because this itself is an open set with none of its boundary points. Okay. Arcs. Number one, a polygonal path is essentially a set of finite line segments with the endpoint of the line segment equal to the initial point of the next. Okay, so just any line segment. So we have one. This here is going to be a polygonal path. A closed polygonal path is where the endpoint of the final line segment is the start point of the first. Okay, so if we were to wrap this round back to the start, okay, in this case, this would be a closed polygonal path. Okay, and the path is going to be simple if it doesn't cross itself at any time. So if instead we had something like this is not going to be simple because the path crosses at this point over here. Okay, and a domain is essentially if it's open and polygonally path connected. That's what we call a domain. Okay. So a couple of examples over here. So we're going to describe the following sets in terms of if they are open, closed, bounded, compact, connected, simply connected, or if they are regions. Okay. So number one, we had the set such that the mod of z is less than 1. So that's going to be something like this over here. Okay. Firstly, it's going to be open because every point inside is an interior point. So we have open over here. This is going to be bounded because we can fit it inside another bigger circle. So that's bounded. Notice this is not compact because the set is not closed and hence it won't be compact. It's going to be connected because any 2 points inside we can join it by like a line. It's simply connected because this set has no holes, and it is a region because this set here is an open set with none of its boundary points. Okay. Alrighty. Let's have a look at the second case. So set 2 is the z in complex numbers such that a real part of z is between 0 and 1. So let's have a look at that. So we have a greater than or equal to at the 0 point, and just a strictly less than at the point 1. So that's going to be everything inside here. Okay. Firstly, notice that this set is not open because this point over here is a boundary point. Okay. And hence, not every single point inside a set is an interior point, and so it's not going to be open. And at the same time, it's not closed because these points here, these boundary points here, they're not included in the set. Okay, so the set doesn't contain all of its boundary points, and hence there's going to be none. Okay. In this case, it's neither closed nor open. Set 2, notice it's not going to be bounded because these go towards infinity and negative infinity at the bottom, so we can't fit the set inside a ball. And if it's not bounded, it's not going to be compact. Okay. Notice it's going to be connected because any 2 points inside a set, we can join it with a line. And it's also going to be simply connected because the set doesn't have any holes. Okay. And this is a region because it's an open set with some of its boundary points, and these boundary points are just the ones on the imaginary axis. So this is going to be a region. Okay. Let's have a look at the third case over here. So the set is just a point. Okay, 1 plus I. That's this point over here. This is not going to be open because the point is not it's not an interior point, and it is going to be closed because this here is just a boundary point. So closed. This is bounded because we can fit it inside a circle, so like this. And it's going to be compact in this case because it's both closed and bounded. It's going to be connected because there's only one single point, so it's going to be connected, and it's simply connected because there aren't any holes. But notice this is a point, and as we mentioned before, regions, the whole point of a region is to exclude points and lines, and hence this is not a region. Okay. And the last case is the annulus. Okay. So that's going to look something like this, where everything inside is shaded. Okay, let me use blue. Okay. So firstly, this set is going to be open because every point is an interior point. So open. This is going to be bounded because we can fit it inside another larger circle. But it's not going to be compact because it's not closed. This is going to be connected because any 2 points, point 1, point 2, we can join it up by a polygonal path. So it's going to be connected. But notice this is not going to be simply connected because we have a huge gap like inside over here. So we have a cross for simply connected. And this is going to be a region because it's an open set with none of its boundary points. Okay. And these are the answers. Okay. Moving on to a bit of complex functions. A complex function is one whose domain or whose range or both is a subset of the complex plane, and it's not a subset of the real line. Okay, so if it's a subset of the real line, that's just going to be a real function, not a complex. And most of the concepts from real analysis, they carry over to complex, such as the domain, codomain, range, image, and pre-image, but with some extra more interesting functions like z going to mod of z and z going to its conjugate. Next part is the fractional linear transformations. These are functions of the form az plus b over cz plus d, where the coefficients are complex numbers and ad minus bc is not equal to 0. Now this condition, we need this condition because if, say, for example, we had f of z equals z plus 1 over 2z plus 2. Okay, then notice this, firstly AD minus BC, it's going to equal 1 times 2 minus 2 times 1, and that's going to equal 0. Okay, so notice that when AD minus BC does equal to 0, we essentially get fz just cancels out to be, well, a half. And this is just a constant function, and we're not really interested in constant functions when we're talking about fractional linear transformations. And that's why we have the condition AD minus BC can't be 0. And if z varies on a line or a circle, then fz also would vary on a line or a circle. Okay. And what happens when z approaches minus d on c? Then we know that cz plus d approaches 0. And when the denominator approaches 0, our f of z becomes unbounded. And hence, since we know a circle must be bounded, f must be a line, because lines aren't bounded. Must be a line. Okay. Now consider the fractional linear transformation t of z equals w equals 1 on z plus I, and we want to find the image of the line 3x plus y equals 1. Okay. Now the game here is we want to use this rule. Okay, we know this rule, and if you imagine we find functions of x in terms of u and v, so f of u and v, and also y in terms of f of u and v, then we can plug these two values straight into this equation here, 3x plus y equals 1, and we essentially have a relationship between u and v, and that would give the image of the set. Okay. So again, firstly, let z equals x plus iy and w equals u plus iv. And if w equals 1 on z plus I, then z equals 1 minus I w on w. That's just rearranging, making z the subject. Okay, and again, why we rearranged it is because we want to make x and y in terms of functions of u and v. Okay, so since we set w equals u plus iv, we can sub that in to the function over here, and we get this. A bit of algebra here, and notice we have a complex in the bottom, so the game here is to multiply the top and bottom by its conjugate. And doing so, we get something like this. Okay. This is just, notice that in the top here, we want to be separating into real and imaginary parts. Okay. So essentially, this part here is the real part of z, and this part here becomes your imaginary part of z, and we equate those with x and y, since we let z equal x plus iy. Okay. Now again, as we said before, since we have functions of x and y in terms of u and v, we can then sub these into 3x plus y equal 1 to get this thing over here. Okay. So rearranging this equation, we finally end up with this thing over here. And notice that's a circle centered at minus 1 on 4i with radius 5 on 4. Okay. Alrighty. And hence, if we just write it formally, T of C is the set over here where that's the circle center, minus 1 on 4i, radius 5 on 4. Okay, example here, if the mod of z is larger than or equal to 2, prove that this inequality is true. Okay. Notice that firstly, if we cross multiply, we essentially want to prove that the mod of z plus to the power 4 plus 1 is bigger than or equal to 15. Okay. And alrighty. And notice that since it goes back. Notice that since we have a bigger than or equal to over here, instead of using the triangle inequality, which gets you the less than or equal to, we want to use the circle inequality that gets you the bigger than or equal to. Okay. So to use the circle inequality, we want to chuck it in a form of the circle inequality, and hence that's going to be bigger than or equal to this over here, and this is by circle inequality. Okay, and since we know that the mod of z is bigger than or equal to 2, this inside thing here is going to be bigger than or equal to 0, and hence we can just remove the outside absolute value. And again, this is going to be bigger than or equal to 2 to the power 4 minus 1 from the given condition over here. Okay, and that's going to equal 15. And we simply take the reciprocal of both sides to get our desired inequality. Okay. Next part is going to include limits and differentiability. So, part 1, a limit is said to not exist if the limit attains different values along different paths. So, if we consider the input over here, we apply f to get an output. Say we're looking at the limit at this point over here. If we have a look at the limit as we approach from this path, and say we get the output is this point over here, but instead, if we have a look at the limit as we approach from this path, and we get, say, this point over here, notice that these 2 points are not the same, and hence the limit attains different values along different paths, and the limit would not exist. Okay. And a limit is said to exist if it's true from the definition. Okay, so definition of a limit: for every epsilon bigger than 0, you can find a delta bigger than 0 such that this thing is true. Okay. Example 7 proved that the following limit does not exist. Okay. So firstly, you can set the z equals x plus iy, or use Euler form, z equals r e to the power I theta. Okay. In this case, we're going to use the Euler form, and we have to re-parameterize the whole limit. So when z approaches 0, our r would approach 0. Okay. And this limit here is essentially fixing a value of theta. Let's say fixing a value of theta, and we want to take r approaching 0, so that's going to approach the origin. If we have a different value of theta, that's going to approach it from a different angle, so that's going to be approaching 0 from, let's say, this angle over here. Okay. And hence, if you sub in z equals r e to the power I theta, we have this limit over here. And just a brief recap, r e to the power I theta is the same as r cos of theta plus I sine theta, so r I sine theta. Okay. So the imaginary part of this component is just the r sine theta as you extract it from over here. So we get r sine theta over r e to the power I theta. The r's cancel out, and notice that our final limit does not depend on r. So this is just going to be the sine theta on e to the power I theta. Okay, and this final value over here, okay, this final value is not a strict number because it depends on theta. So essentially, if we alternate theta, we get different values for the limit, and hence, since we get different values for the limit does not exist. Okay. Moving on to continuity. A function is said to be continuous if and only if the limit at that point is just a function value, f of a. Okay, so the limit as z approaches a, f of z is just f of a. The sums, products, quotients, compositions of continuous functions, they're always going to be continuous for wherever they're defined, and that just carries over from our real analysis. Okay, example 7, this was in the class test. Prove that f of z equals the imaginary part of z is continuous for all z being in the complex numbers. Okay. Now, essentially, we are required to prove that the limit as z approaches z0, f of z equals f of z0 for all z0 being in the complex numbers. Okay. And to prove a limit, we have to go to the definition of a limit. Okay. So essentially, for all epsilon being positive, we need to find a delta such that this thing here is true. Okay. So, since we have a for all delta being positive, we want to let delta be bigger than 0. And the game is to find a delta, but essentially we don't really know what delta can be right now, so we can just leave it blank for now. And this part here is the if part of the proving statement. So we want to suppose this thing is true. And this part on the right is the then part, and that is essentially what we're trying to prove. Okay. So if we sub in fz equals m of z, we get this thing over here, and we can combine it into m of z minus z0. Okay. And that's going to be less than or equal to the modulus of z minus z0. Just a quick geometric proof for this. So if this is the number z, then the length is going to be the modulus of z. And the imaginary part of z represents this length over here. Okay. And we know that the side of a right angle triangle is always going to be less than or equal to the imaginary part. Sorry, the modulus of z. So the side of a triangle is always going to be less than or equal to the hypotenuse, and hence the imaginary part of z is less than or equal to the modulus of z. Okay. And that's how we get this jump over here. Now, this is going to be less than delta, and that's just simply from our if condition. Okay. But we want to make it less than epsilon. Okay. That's what we're trying to prove. So, essentially, if we set delta to equal epsilon, then we're pretty much done. Okay. All we need to do is go back to our proof where we choose delta equals something, and we set delta to be epsilon, because we know if we set delta to be epsilon, this whole proof works out, satisfying the then condition. Okay. Hence, the limit is equal to the function value for all z0 being in the complex numbers, and hence f of z is continuous for all z in the complex numbers. Okay. Moving on to differentiability. A function is differentiable if the following limit exists. Okay. And again, if a function is differentiable, it must also be continuous, and that carries over from our real analysis. Okay. Moving on to Cauchy-Riemann equations. So if we sub z into z equals x plus iy into the function, we get functions of u and v in terms of x and y. Okay. it's going to be differentiable at an interior point x equals x plus iy if and only if the partial derivatives, they all exist and are continuous, and these conditions hold. Okay. So Cauchy-Riemann equations, they give us a nice way of checking where a function might be differentiable. And the derivative is given by this formula over here. And a quick recap, u subscript of x, that just means the partial derivative of u. Oops. The partial derivative of u, I don't know why it's doing that. With respect to x, okay? And same with v of x, so u of y. That's partial u on partial y. Alright? Okay. Some quick examples. Where are the following functions differentiable? And in this case, we're going to be doing our Cauchy-Riemann equations. Okay. So firstly, we need to sub z equals x plus iy. Okay. And we want to be separating into real and imaginary parts. That way, we can use the Cauchy-Riemann equations. So u equals the imaginary, u is the real, v is the imaginary. And hence, by the Cauchy-Riemann equations, if we compute the partials, we get these four equations. Okay. Now, condition 1 of the Cauchy-Riemann equations was the partial u, partial y must be the negative of partial v, partial x. Okay. So if we equate those two, we get xy must equal to 0. And condition 2 was that partial u, partial x must equal partial v, partial y. Okay. So equating those two, we get x must equal plus minus y. Okay. Now, since these two conditions must hold simultaneously, so we need an AND. Okay. If we just consider the graph, xy is the simply just represents the real and imaginary axis. Okay. And x equals plus minus y represents these two lines. And essentially, since we have an AND relationship, we're going to be finding the intersection between these two. Okay, and the only point of intersection is the origin. And hence, x equals y equals 0 is the only solution, and f1 is only differentiable at the origin. Okay. Part 2, we have this thing over here. So, using Cauchy-Riemann equations, again, we have the real equals x cubed, imaginary equals y cubed. Okay. And again, compute your four partial derivatives. And the first condition, again, is partial u, partial y is the negative of partial v, partial x. Well, 0 is always equal to minus 0, so this condition is always true no matter what x and y are. Condition 2 is partial u, partial x must be the same as partial v, partial y, and that implies that x must equal plus minus y. Okay. So since condition 1 is always true, the differentiability of a function f only depends on condition 2, where x equals plus minus y, and hence f2 is differentiable at point z, where x equals plus minus y. And question 3, we have the function is mod of x plus I mod of y. Again, our real part is mod of x, imaginary part is mod of y. And by the Cauchy-Riemann equations, we have these four equations. Now, quickly, to differentiate an absolute value, notice that absolute value we can consider as square root of x squared. And if you were to differentiate this, we get 1 on 2 root x squared times the chain rule, which is 2x. And this is going to equal to this, which is essentially x on mod of x. Okay. Now, one other way you can consider it is the mod of x, absolute value, I should say, is just this function over here. So the derivative of that is just going to be minus 1 when x is negative and 1 when x is bigger than or equal to 0. Sorry, strictly bigger than 0. Okay. Now again, condition 1 is that we need the partial u, partial y must be the negative of partial v, partial x. Again, 0 is always minus 0, so condition 1 is always true no matter what x and y are. Condition 2 is we need partial u, partial x to be partial v, partial y. Okay. And we get this thing over here. Of course, we know that x and y can't be 0 because of the denominator issues. Okay. And hence, x and y must be bigger than 0, simply because notice that absolute value of a generic number is just a when a is bigger than or equal to 0, and it's minus a when a is less than 0. Okay. Holomorphic. So suppose omega is an open subset of C, and if a function is differentiable in that open subset omega, then we say that f is holomorphic, and we can represent that using this notation over here. Okay. And a function is holomorphic in C, that would be called entire function. Okay. Second, a function can only ever be holomorphic on an open set. So if we have a function that is differentiable on a closed set, it is not going to be holomorphic because the set is closed. Okay. And harmonic functions, so if D is a domain in R2, a function of two variables u is going to be harmonic if and only if it satisfies the Laplace equation, and all of the first and second partials exist and are continuous. Okay. And the harmonic conjugate of u is a function of two variables v such that f of u plus iv is holomorphic. Okay. Okay. A quick example here, show that u equals sine x sine y is harmonic, and find a harmonic conjugate. So firstly, let's calculate the partial derivatives. So partial squared u partial x squared is going to be minus sine x sine y. And let's do the same for y. We get sine x sine y. Okay. Now, if we sum them up, they're going to equal 0, and hence that's going to tell you that u is harmonic. Okay. Now, for finding the harmonic conjugate, we want f equals u plus iv to be holomorphic. And for f to be holomorphic, we need the Cauchy-Riemann equations to be true. Okay. Now, solving the first, differential equation, we get v equals cos x cos y plus c of x. Okay. Since we were integrating with respect to y, our constant function can also be a function of x. Okay. To find c of x, we differentiate this function again, but with respect to x. Okay, and we equate it with our second Cauchy-Riemann equations over here. Okay, and that's going to tell you that c dash of x is going to equal 0, and hence c of x is just a real constant. Okay, hence a harmonic conjugate is this over here. Of course, you can say plus c, where c is any constant, but we just want to find a harmonic conjugate. So if we just set c equals 0, that makes our life the easiest. Next part is the exponential function, and the exponential function is defined by the Taylor series. Okay. If we have the x of x plus iy, we can separate it out into e to the power x times cos plus iy. Okay. And the exponential function is periodic every 2 pi I and k, mainly because this function over here, cos y plus I sine y, that is periodic every 2 pi times, because when you go around the unit circle. Okay. Hyperbolic functions, they're also defined in terms of the exponentials, which in turn is defined in the Taylor series. Okay. And common properties, these are your compound angle formulas. So cosh z plus w is just cosh w cosh z cosh w plus sine z sine w, and same with sine. And these all carry over from our real compound angles. Okay. And if you diff cosh, you get sine, and same if you diff sine, you get cosh. Okay. So these all carry over from our real coshes and sines. Okay. Properties, cosh is going to be even, sine is odd, so we get these two equations over here. And notice again, these also carry over from our real functions. Cosh is periodic every 2 pi I k, and same with sine. And mainly because cosh, remember cosh of z is the same as e to the power z minus plus e to the power minus z over 2. And we know that our exponential functions here, they're periodic every 2 pi I k. So essentially the periodicity of cosh is inherited from the periodicity of our exponential functions. Okay. Lastly, this one also carries over from our real analysis. So cosh squared minus sine squared equals 1. Our trig functions, they're also defined by exponentials, okay, and which in turn they're defined by our Taylor series. Okay, and some useful properties: sine of iz is I sine z, sine of iz is I sine z, cosh iz is cos z, and cos of iz is just cosh of z. Okay, these are some useful properties when you're simplifying your answers down. Logarithm, the principal branch of the logarithm, denoted with the capital L, is defined by ln absolute value of z plus I principal argument of z, again with the capital A. Again, arg of z is the principal value, and the log z is differentiable on all of the complex numbers minus the negative real axis and 0. And this is because we know that the arg of z is not continuous there, and hence the log can't be differentiable. Okay. The multi-valued logarithm denoted with lowercase l, that's just the same except with the lowercase a. Okay. Arg of z, that's the principal arg of z plus 2k pi, and hence the multi-valued log is just the principal log plus 2k pi I. Okay. Example, solve cosh of z equals -2. Okay. Now, if we just use this using real analysis, notice cosh of z is something like this, where the minimum is at 1. -2 is over here. Okay. And hence, we know that there's not going to be any real solutions because the cosh of z does not ever go to -2 if we're just looking at the real numbers. Okay. So the trick here is to convert cosh into e to the power z plus e to the power minus z on 2. Multiply the 2 across and multiply both sides by e to the power z, and that way we get a quadratic in terms of e to the power z. Okay, and we can always solve quadratic equations. Just whip out your quadratic formula and we get this thing over here. Now, e to the power z equals -2 plus minus root 3. We can take the log of both sides, and this is going to be the multi-valued log, which is defined by ln absolute value of that over here, plus the I-arg of the second number. Okay. Now, -2 plus root 3, that is going to be both negative, so -2 plus minus root 3. Both branches, they're always going to be negative numbers. Okay, and hence the argument of -2 plus minus root 3, they're both going to be pi plus 2k pi. Okay, and that's where we get these solutions from. Moving on to some branches of a logarithm. So for any real number theta, a branch of the logarithm is defined by log subscript theta equals ln absolute value z plus I arg of z. Okay, but the arg of z, it's going to be between theta and theta plus 2 pi, and that's what we define as a branch of a logarithm. Okay. And the point z equals 0 or arg z equals theta, that's going to be the branch cut. So no matter what branch you take for the log, there's always going to be a branch cut, the set of points where this is not differentiable. And the log of z is again differentiable everywhere except on the branch cut. And if you take the derivative, you just get 1 on z. And that again carries over from our real derivatives. Okay, example over here, define a branch log of theta of the multi-valued function log of z such that we want it to be continuous at -1 and it has a value of 7 pi I there. Okay. Now, firstly, the principal branch is not continuous at -1, and hence we can't use that branch. Okay. So let's consider where we take the branch cut along the positive real axis. So if you have a look, this means that it's not going to be differentiable along this part here, which makes it's going to be continuous at -1. Okay. And hence, from definition, that's going to imply that arg of z is between these two values, and our game here is to find the value k such that we have the 7 pi I at -1. Okay. We're given that the log theta of -1 is, again, this is defined as ln absolute value -1 plus I arg of -1. ln of 1 is just going to be 0, so that goes away, and hence we get the I arg of -1. And this is going to be 7 pi I. Okay. So essentially, we want arg of z to vary between 6 pi and 8 pi, because that way this generates out the 7 pi I when we compute log of minus 1. Okay. This gives us that theta must be 6 pi. Okay. And hence the branch is defined as this thing over here. Log base of 6 pi z. Okay. And that would give us that the value at minus 1 is going to be 7 pi I, and it's also going to be continuous at minus 1. Okay. Next example, determine where f of z equals log of 3iz minus 4 is differentiable. Now, we know that the log function is differentiable everywhere except on the negative real axis and 0. So, we know that f is not going to be differentiable when this thing is true, okay, where we set lambda to be between minus infinity and 0. And so, if we rearrange for z, we get z equals minus I on 3, 4 plus lambda. Okay. So essentially, if lambda is in the set minus infinity to 0, minus 4 plus lambda on 3, that's going to be in the set minus 4 on 3 infinity. Okay. And hence, if z equals ik, then k is going to be in the set between minus 4 and 3 and infinity. Okay, so this is the branch where the imaginary axis, so from minus 4 and 3i going upwards, and these are the set of points where the log, this f of z, is not differentiable. Okay. And next example over here, we have find all the complex numbers z such that the sine of z equals 2. Okay. Again, if you're looking at the real numbers, we know that sine minus 1, sine of x is bounded between minus 1 and 1. So if you're just looking at the real numbers x, there's not going to be any solutions for when sine of x equals 2. Okay. Again, we did a trick where sine z, we rewrite it as e to the power iz minus e to the power minus iz over 2i. Okay. And the game here is to rewrite this equation in terms of a quadratic equation, because we can always solve quadratic equations. Okay. By just whipping out the quadratic formula. Okay. And we simplify this down to 2i plus minus root 3i. And if we take the log of both sides, we get this equation over here. And recall that the log of a complex number is defined by the ln absolute value plus the I argument. Okay. So if we have a look at solving the first branch, okay, absolute value of, sorry, the modulus of this first number here just turns into 2 plus root 3, okay, and the argument of 2 plus root 3i, this complex number is going to lie somewhere over here. That's going to be pi on 2 plus 2k pi. Okay. And hence, if we rearrange for z, we get our first set of solutions, this thing over here. And if we look at the second branch, so instead we had the negative inside. Okay. Again, the modulus of this whole complex number turns into 2 minus root 3. Okay. And if we have a look at the argument of 2 minus root 3i, so 2 minus root 3, this is still going to be a positive number. So 2 minus root 3i is going to lie somewhere over here. Okay, and again, the argument of that is again going to be pi on 2 plus 2k pi. So rearrange for z, we have the second set of solutions. Okay, so these are the first set, these are the second set, and where we know that k must be an integer. Okay. Alright. Next part is going to be on the complex powers, and I'm now going to be handing this over to the second part, which is done by Ronald. Okay.
Okay, hello. Welcome to the second half of our first part. Just a reminder that we will have a second part on Thursday. And yeah, let's just get started. Thank you so much to the amazing, brilliant, and smart as hell Fred. And we'll just get started with complex powers. So if we want to calculate the complex power, which is just a complex number to a complex number, in this case it's a complex number z to a complex number alpha, we can use the fact that z to the alpha can be expressed as the exponential of alpha times log z. And of course, if we expand this, since log in this case is multi-valued, we have the exponential of alpha times the principal of log z plus 2i pi k alpha, and k is some integer. And of course, the principal value is just the exponential of alpha times log z, where log is the principal log. And of course, that just means if we want to transform our multi-valued power into a principal value, we just have k equals 0. Now we also have complex roots, where z is put to the power of 1 over some natural number, or well, of course not natural number, some positive integer, and we have the principal value being equal to the modulus of z to the nth root, and then we have that multiplied by the exponential of I times the principal argument over n. And of course, if z is equal to 0, we define the root to also be equal to 0. Now, let's calculate some complex powers. We have I to the power of 2 minus I, and of course we can just put it into the form that we saw right here, so the one right here. And so of course we have alpha as our 2 minus I, and we have it here, so we have the exponential of 2 minus I, and that's multiplied by the log of our base I, which is right here. And then what we can do is we can use the fact that the modulus of I is just 1, right? So this just becomes ln of 1, and of course ln of 1 is just 0, and so all we're left with is this imaginary part right here. And so what we can do is we can just multiply this complex number by the I times pi on 2 plus 2k pi, and of course what we get is this exponential right here. And then what we can do is we can just split it up. So first we can multiply this 2 into the pi on 2 and the 2k pi, and then of course we can split up the real part and the imaginary part. And what we would get is we have the exponential of pi on 2 plus 2k pi, and then we have the exponential of I times pi plus 4k pi, and of course this is actually just equal to -1, so we have the power being equal to minus the exponential of pi on 2 plus 2k pi, and so that's our first part done. But of course we also want the principal value, and so the principal value can just be from the fact that k is equal to 0, we sub in k equals 0, and what we get is the principal value of I to the 2 minus I is equal to minus the exponential of pi on 2. Okay, so we have this question right here. We want to find where this function f is analytic and where it's continuous. So f is defined to be the principal value of the root of z squared plus z to the minus 2. Now, what we can do is we can first just look at the normal square root. So our normal square root is given by this function that we've defined previously, except instead, of course, we have a 2 in here instead of an n. And of course, we can just look at its properties. The main properties are that since arg is involved, it's not differentiable on this line from 0 to minus infinity inclusive. And so it's differentiable everywhere else. And then we know that the square root is also continuous at 0. So it's continuous everywhere except the line from 0 to infinity where it does not include 0. And of course, this is true for all principal value roots, and you can just call it whenever. Now, what we can do is we can put z in terms of polar form, so r e to the I theta, and the reason we do that instead of Cartesian form is because we just want to have our powers be incorporated into the complex numbers that we find. And what that allows us to do is we can factorize by cos 2 theta and sine 2 theta. And then what we can do is we know that we want to find out when it's going to be on the negative axis of the real axis. So what we can do is we can find out when the complex number is going to be real. And so to be real, we have to have our imaginary part right here be equal to 0. And if we solve for that, we actually get r equals 1 from our r squared minus 1 on r squared. And we get 2 theta being some integer times pi from our sine 2 theta. So what that means is it can either be on the unit circle or it can be on the imaginary axis. And of course, we don't include 0. The reason we don't include 0 is because we have a z to the minus 2 here. So obviously, the function is not defined when z is equal to 0. And so we can first look at when it's on the imaginary axis. So we have z equals it, where t is some non-zero real number. And then we can substitute it into z squared plus z to the minus 2. And of course, what we see is since t is real, t squared is also greater than or equal to 0. And so what we get is minus t squared minus 1 on t squared is less than 0. Now, we can also consider when it's going to be on the unit circle. So we have z being equal to e to the I theta, where r is just equal to 1. And then we can put it into z squared plus z to the minus 2, and we get 2 cos 2 theta. And so we want to know when it's either negative or 0, and we can just observe the cos graph, and we would find that it's when theta is in between pi on 4 and 3 pi on 4, and of course we can just add multiples of pi to it. So we know that the principal value of the square root of z is differentiable everywhere except on the negative real axis. And so what we can do is we know that the z squared plus z to the minus 2 is on the imaginary, it is on this negative real axis if they are either on the imaginary axis, which does not include 0, or when they're on the unit circle and their argument is in this domain. Now what we can do is we can call this set A and just formalize it. So this just means all complex numbers which are on the imaginary axis, not including 0. And this means all complex numbers which are on the unit circle where their argument is in this range. So Of course, as I mentioned before, we have a z to the minus 2, which means f is not defined at z equals 0. If it's not defined, it's not differentiable there. So what we can say is f is analytic on everywhere except at a and at 0. So we also want to know when it's continuous, and the main difference is that it doesn't include the points where the inside is equal to 0, so let's just calculate where it's equal to 0. And so, of course, we have z squared plus z to the minus 2 equal to 0. We can just move this over to the other side, and we multiply both sides by z squared. And so what we get is the fourth roots of unity for minus 1. So let a0 be a, not including the fourth roots of unity of minus 1. And so what we get is the set where z squared plus z to the minus 2 is on the negative imaginary axis, and it does not include 0. So we know that f is continuous. Sorry, give me a sec. So f is continuous on the complex plane, not including a0 and not including 0. So now we've moved on, we're going to start doing curves and then move on to integration. So a curve is just a continuous function which takes a parametric and transforms it into a complex number, and of course the main thing is that it's continuous. So a curve is essentially just any path on the complex plane. These are some possible examples. And of course we have an initial point and a final point. A curve starts somewhere, travels, and then it stops somewhere, and it has a parametric which ranges from a to b, and we define the curve at t equals a to be the initial point and t equals b to be the final point. It also has a range, and that's every single possible point which the curve has, and of course you can just think of it like a range in the real functions. It's essentially the same, except of course each point is complex, so we have a range which is a set of complex numbers. And then of course we have some properties. So a curve can be closed, simple, or a Jordan curve, and we'll just explain what this means, but this is just a formal definition. Of course we'll have the slides uploaded, so if you want to look at the actual formal definition, you can do that in your own time. But essentially, we want to try to classify these kinds of curves because it's very important to know what type of curve you're dealing with when you integrate. So we have a couple properties. The first property is that it's simple. It essentially means that it does not cross over itself. There's no point where a later t value will be at that same exact point. And we have closed curves, which essentially just mean that they have the same initial and final point. So the first curve is simple because it doesn't cross over itself, right? It's just going like that. Oops. Just goes like that, and of course, obviously it doesn't cross over itself, but since it has a distinct initial and final point, we say that it's not closed. And so we can look at the second curve. Obviously it crosses over at this point, so we say that it's not simple, and of course it does look like it's closed since you can't discern a initial and final points. And of course the third curve is going to be both. It's both simple since it doesn't cross over itself, and it's also closed. And if it's both simple and closed, we call this a Jordan curve. So we have some definitions. We have something called a join, which is essentially if we have two curves, we can as the name suggests, join them together. So let's say this is our first curve, and this is our second curve. And the main condition that we need for a join to be possible is that the ending point of the first curve has to be equal to the starting point of the second curve. And this is just the piecewise function that represents this curve, and it uses this symbol right here. So there's also a reverse curve, which is essentially the curve has a starting and end point, but it also has a direction that it travels in, because the direction that it travels in is based on how the point moves when t is increasing. So of course the reverse curve, as the name might suggest, essentially just has the same curve, but it travels in the opposite direction. So parametrization is a very key concept. It's going to be used in integration a lot, and we'll see how it's used later. But there are two main types of curves that we need to know how to parameterize, and the first is a straight line. So let's say we had a straight line from some arbitrary points. Let's call them z0 and z1. So we can define it to be a gamma t, which is equal to z0 plus t z1 minus z0. And you might notice that this is actually just the parametric form of a line, where the starting point is z0. So if you sub in t equals 0, this becomes a 0 right here, so we're left with z0. And then of course if t is equal to 1, we get z1 minus z0. These cancel, and so in the end we get a z1. And so what that means is it's a line, it starts at z0 and ends at z1, and of course it's a straight line. So we also have a parameterization of a circle, and it has a center at z0 and a radius of r. So r is a real number and z0 is a complex number. So this is actually quite simple. We can just build up to it. So first we have e to the it, and since t ranges from 0 to pi on 2, pi to 2 pi, we just get a unit circle, right? And then we have the r here, which just means that we make the radius r instead of 1, and then a plus z0, and what that means is we just make it so that we have the origin here, and then we move our center to z0. And so the parameterization is gamma of t is equal to z0 plus r e to the it. And what you'll notice is that, of course, gamma is the go-to letter that we use when we want to represent a curve. So let's say we have a curve, and we can split it up into its real and imaginary parts, which are gamma of 1 and gamma of 2. The derivative of the entire curve is just the derivative of the real part and the derivative of the imaginary part. And of course, it's just right here. Then we can say that gamma is continuously differentiable if the derivative both exists and is continuous on every point between a and b. Then we can also say it's smooth if gamma dash t is never 0 and it's continuously differentiable. Then we can say that gamma is piecewise smooth if it's a join of finitely many curves and each individual curve is smooth. So let's just quickly look at an example of what a join is and what a piecewise smooth curve is. So this is a join of 4 different curves. So we have C1, C2, C3, C4. And what we notice is that the endpoint of C1 is equal to the start point of C2. The endpoint of C2 is equal to the start point of C3. And the same is true for C3 and C4. Now, we also see that obviously this is smooth right here. C2 is also smooth, C3 is smooth, C4 is smooth. So it's made up of 4 joins, which is obviously finite. And so 4 joins together, that just means that since each individual curve is smooth, we can call this piecewise smooth. And obviously we can't call it actually smooth because it's not smooth at these points right here. So where the joins occur, it's not smooth because the derivative is not continuous. And so essentially what it means for a curve to be smooth is to ignore all of the cusps and ignore all of the sharp corners. So let's consider this curve gamma 0 of t, where t it's equal to t plus it, and t ranges from -1 to 1. So obviously that's a line from -1 minus I to 1 plus I, and since it's a line, obviously that's smooth. Believe me, that is a line, trust me, okay? So then we can also define a gamma of t, which is equal to t cubed plus I times t cubed. So, is it smooth? First, what we can do is we can just sub in the points. So we know that it ranges from -1 to 1. If we sub it in, we get gamma of t is, so gamma of -1 is going to be equal to -1 minus I, and gamma of 1 is going to be equal to I plus I. Sorry, 1 plus I, and of course what we get is the same curve. It still represents a line from -1 minus I to 1 plus I. So, first let's just take the derivative and see where it's equal to 0, because obviously the most foolproof way to find out whether something is smooth or not is just use the definition. So, we know that when t is equal to 0, the derivative is equal to 0 as well, and if the derivative is equal at any point, gamma is no longer smooth. So something to note is that if a curve is smooth, it's not piecewise smooth either. So, as I mentioned before, gamma 0 and gamma both share the same overall curve. But if we look at this example, where of course it starts at -1, and we have 2 points, the red point is going to be our t plus it, and the orange point is t cubed plus it cubed. We actually see that there's a noticeable pause at 0. So our orange point right here isn't continuously smooth like the red point. The red point's just continuously moving, but our orange point right here has a pause right here and then keeps going. So what we actually see is that not only does it matter that there are no like cusps or sharp corners, it also matters that the point is continuously moving. So we have the length of a piecewise smooth curve being given by the integral from a to b of the modulus of the derivative of gamma. And let's just look at why that is. So the length of a curve, let's say that this is a curve right here, can be approximated by 2 points, and then we can just draw a line between them. And then of course we can draw out these. This is just the change in x with respect to time, and this is the change in y with respect to time. And so the hypotenuse of this right angled triangle is going to be approximately equal to the arc length. So if we just work that out, we have the square root of x dash t all squared plus y dash t all squared. and that's going to be equal to the hypotenuse, but that's also going to be equal to the modulus of gamma dash t, because gamma dash t is of course equal to x dash t plus I y dash t. So, of course, the reason we integrate it is because we want to get a smaller and smaller change in x and change in y, which would let us integrate to find the arc length. So, let's just look at this example. We have a curve right here, which is gamma of t is equal to r e to the it. That's just a circle with radius r and center at 0. So, please keep in mind that the curve ranges from 0 to 2n pi, right? So we have r being greater than 0, and we just take the derivative. So the derivative actually does function the same as a normal derivative. We treat I as a constant, so we have I chucked down here as a coefficient, and so y gamma dash t is going to be equal to ri e to the it. Then of course we want to sub it into our length formula. We have it ranging from 0 to 2n pi, and we have the modulus of the derivative. So we know that I has a modulus of 1, and e to the it has a modulus of 1. So in the end, it's just r, and of course it's r because r is greater than 0, so it's positive. And so we can just integrate it, and we should get 2n pi times r. So we have a contour right here, and essentially a contour is a range that we integrate across, and the range of which is a contour can be traversed in some manner. So essentially there's a direction that the contour can travel in, and if it's simple, it can either traverse in a clockwise or anti-clockwise direction. And if they don't mention a direction, we can assume that it's going in anti-clockwise traversal. So there is a difference between a contour and a curve. A curve is a function, whilst a contour is a range, but can be represented by a function. So we have the integral, the complex integral, and if we can split up some function f into its real and imaginary components, we actually see that the integral of f is equal to the integral of the real part plus I times the integral of the imaginary part. And of course the rules of real integration apply, since we just treat I as some constant, right? A complex number is just a scalar, just like any other real number. So you can treat them as such in this integration. And there's some useful properties that we want to know. And essentially, the real part of the left-hand side is equal to the integral of the real part of the function. And the real part of the integral is equal to the integral of, the imaginary part of the integral is equal to the integral of the imaginary part of the function. So there's also some properties that real integrals share with complex integrals. So obviously the complex integral is linear. The complex integral can have substitutions. We can apply by parts, and we have this property right here which can be useful, which is the modulus of the integral is always less than or equal to the modulus of the function inside this integral. So all of these you might have seen in like 1a or 1b, so they shouldn't be too bad. And so one of the uses of complex integration is something like this, which you can do through something like by parts, can be simplified. So what we can do is we can notice that cos of t is equal to the real part of e to the it, And we also know that e to the t is real since t is real. So e to the t cos t is going to be equal to the real part of e to the t times e to the it. So essentially the reason we do this is because we know that exponentials are very easy to take the integral of. So we have our original integral and we transform it so that we have the integral of the real part of this complex function, and then we can take out the real part. So we want to find the real part of this integral of this complex function. So what we can do, we can put the real function together and put it into one exponential. So we have e to the 1 plus I multiplied by t. And of course, we can treat 1 plus I as any other constant. So when we integrate, we just divide by 1 plus I. And then we have 0 and 2 pi to sub in. We can sub it in. So what I did was I just transformed this denominator into this number right here. And we also subbed it 2 pi and 1 minus 1. So what we can see is that this is actually equal to e to the 2 pi plus I 2 pi. And of course, that's just equal to e to the 2 pi, e to the I 2 pi. E to the I 2 pi is just equal to 1. So in the end, it's actually equal to e to the 2 pi. Now, we can take the real part of both sides. We know that this whole thing is real and this is real, so we can just multiply them together. And what we would get is that the original integral is equal to e to the 2 pi minus 1 all over 2. So we can also define a complex line integral, which is essentially just having a u sub where z is equal to gamma of t, and gamma of t is a function representation of our contour gamma. Just give me a sec. So what we see is that the integral is actually linear as well right here. And the reverse, this is integral. So if we have a contour and we wanted to integrate it, the integral of its reverse is going to be the negative. And then if we have two curves, let's say alpha and beta, and then they add up to be one big curve gamma, the integral of gamma is equal to the integral of alpha plus the integral of beta. Now, we have an example right here, which is just the integral of z squared dz, and the contour is going to be the unit circle. So, oh yeah, one thing I forgot to mention is that whenever we're doing contour integration, you won't see a number down here and number up here. Instead, you'll just see a representation of some curve, and the main reason is because in real integration, we integrate between 2 points, but there's only one way to get between these 2 points since we exist on a larger real axis. But when we add in the imaginary axis right here, we can actually traverse this through any number of paths. So this is just to consider what path that we're traveling in. So what we do is we find the parametrization of our contour. Our contour is the unit circle, so we know that that's going to be e to the it. And of course it ranges from 0 to 2 pi. And we have the derivative, which is I times e to the it. And so we can evaluate this integral, and what we would get is we sub in our gamma, and we also multiply it by our derivative of gamma. And so what we get is an integral that ranges from 0 to 2 pi. and then what we can do is we can chuck this 2 into the power, and we can simplify it by combining these two exponentials, and what we should get is the integral of I times e to the 3it. Of course, 3I is considered a scalar, so we can just divide by 3i, and what we should get is, oops, there should be no I there, because the i's cancel. We get the exponential of 3it on 3, where we have to sub in 0 and 2 pi. And so if we do that, we get 3i times 2 pi minus e to the 3i times 0 all over 3. This just becomes e to the 6 pi I, which is obviously 1, and this becomes e to the 0, which is also 1. 1 minus 1 is 0, so we get 0 as our final answer. Now, we have this integral right here, which is z bar, and we want to integrate it by the contour that's given, which is gamma is equal to t plus it squared, and t ranges from 0 to 1. So what we can do the complex line integral, and we just substitute in our gamma of t and derivative. So obviously our our gamma of t is equal to 1 plus 2it, because we're taking the derivative of the real and imaginary part individually. And then we just sub it in. So we subbed in our gamma and our gamma dash t. And so what we get is the integral of t plus it squared conjugate times 1 plus 2it. So, of course, we can just apply our conjugate first, and then we can multiply these complex numbers. And so what we should get is a cubic, and you should know how to integrate a cubic. And in the end, we should get 1 plus I on 3. So, not too bad. There's a problem, right? So what you might have noticed is that we actually can have multiple parameterizations, but they represent the same curve. So we did an example where that was true. Another example is right here, where we have gamma of t equals to t, and that's a line from 0 to 1, obviously. But this is also a line from 0 to 1, except it has a different function and a different range. Sorry, a different domain. So we have multiple different curves. They can represent the multiple different parameterizations of the same curve. So we can formalize this. That's basically what it means. It means that we can have many different ways to represent the same curve through t. And the more important part is that the integral of any two parameterizations which represent the same curve will be equal. So the integral of our gamma right here and our delta right here, since they both represent the same curve, is going to be equal. So what we have is we have gamma as a piecewise smooth curve and f to be a complex valued function, and it's defined on the range of our contour gamma. We can have our L be the length of this contour and M be a maximizer. And a maximizer is just the largest modulus that can exist on our function f. So this might seem a bit weird to you. Why is this true? We can just dumb it down to our real function. So let's say we have a real curve right here that we're integrating. And so we're integrating from this part A to this part B. Obviously, the integral is always going to be less than the highest point as our height. and our width being the length of the path that we're integrating, which is from A to B. So this rectangle right here is always going to be larger than our integral. And this is kind of the same in complex integration, but instead we're integrating along a path. So you can think of the path as a fence, right? Each individual point has some sort of height, which is its modulus, and we can take the highest modulus and multiply it by the length of our curve, and what we should get is just the largest possible area that the fence can take up. So, using the ML lemma, we just want to prove that this function's modulus right here approaches 0 as r approaches infinity. So, we can have gamma, which denotes a circle from 0 to pi, so obviously that just means a semicircle with radius r. So what we can do is generally we want to find a maximizer, and you've probably done this before. We essentially just have to find some real number such that it's bigger than the function inside here. So obviously what we can do is we can take the modulus of the inside, and then we have z to the 4 plus 1, which is our denominator. We know that from the circle inequality that's greater than or equal to the modulus of z to the 4 minus 1. And so since we have the modulus of z being equal to r, we have this inequality right here. And then of course we can take the reciprocal, and if we do, the sign flips, and we get this real number right here is greater than or equal to every single possible number that can come out of this function right here. And so we can then just take the arc length of gamma. Since it's a semicircle with a radius of r, that's just pi r. And so by the ML lemma, we can multiply pi r with 1 on r to the 4 minus 1. And obviously, as we take the limit of r approaching infinity, since we have a larger power on the bottom, we know that it's going to always approach 0. So we've proven that the result is true, and that's how you use the ML lemma. Then we have something called the contour integral. Essentially what it means is if we have a contour that we're integrating with, it's always going to be equal to any parametrization that we do. So this might be a bit obvious. It's essentially just a continuation of our former theorem, which basically said any two parametrizations of the same curve would result in the same integral. And so obviously the integral is dependent on the curve rather than on the actual parametrization. So now we have something called Cauchy-Gaussat theorem, which is essentially if we have a simply connected domain, which means a domain that has no holes in it. So obviously it's defined everywhere inside. And we have a function that's holomorphic on this domain. And then we have a closed contour. In this domain, we have the integral of the function f along the contour gamma being equal to 0. And an extended version is essentially if we have a large contour and it has a bunch of holes in it, let's call the holes gamma 1, gamma 2, gamma 3, and this boundary gamma 0. The integral of this boundary right here, so the outside, is always going to be equal to the integral of each individual hole right here. And so we have this boundary being traversed anti-clockwise, and in this case these smaller contours are also being traversed anti-clockwise. So we have this curve right here. We have gamma being equal to the unit circle, and we want to integrate 2z over z plus 1 minus I. So we know that it's going to be holomorphic everywhere except when the denominator is equal to 0. So the denominator is equal to 0 when z is equal to minus 1 plus I. So we want to avoid that, but luckily if we take the modulus of z where it's equal to this, we get root 2, and obviously root 2 is greater than 1, so it's outside the unit circle. So one of the conditions is that you have to have the function be holomorphic on the contour and inside the contour. So obviously since this is outside the contour, it doesn't have anything to do with the actual contour and its insides, which is why by Cauchy-Goslar theorem, we can say that the integral is equal to 0. So we also have something called independence of contour. It basically means that the integral is actually dependent on the starting and ending points. So if we integrate it from this point to this point, it doesn't matter what path we choose. These will all have the same integral. So we also have something called a primitive. You might have seen this in the real integrals. It's essentially just, using antiderivatives. So if we have some function capital F, which has a derivative of f, and we want to integrate small f along a gamma, we know that gamma ranges from a point P to a point Q. We can just have the capital F of Q minus the capital F of P. And of course, that's just akin to normal integration that you're used to. So let's say we wanted to find the primitive of this function right here. And so what we do is we would first integrate it. We know that that's equal to 1 on z minus 1. So obviously that would be a log, right? Well, there's something we need to consider, and that there's a restriction to the contour. And the contour is when rz is less than or equal to 0. So it means that it can only exist on this half of the plane. And also, we know that it's going to be from I right here to minus I. So we want to find a primitive which is able to fit this definition. And the main reason we can't do this is because obviously any contour we draw will have to at some point cross where the principal value log is not differentiable. So to fix that, we can just find another branch of log. We just need a branch of log which does not affect any point in this plane where the real part of z is less than or equal to 0. So what we can choose is we can choose the log 0, which is just a logarithm with the branch cut being here instead, which means that it's differentiable everywhere here, which allows any contour which fits under this definition to be calculated. And of course we have our log 0 of z minus 1 being equal to ln the modulus of z minus 1 plus I times the argument of z minus 1, and the argument ranges from 0 to 2 pi. So, of course, what that means is it's going to be having a branch cut from 1 to infinity, which does not concern us, so that's absolutely fine. And so we have the log being differentiable everywhere except the line 1 to infinity, which is what we want. So we know that this is a fit primitive for our integral. So one thing to note is that we have our point 1 here. We can actually choose any branch cut that we want, but the main reason we chose this one is because it's much easier to calculate, as we'll see later. So we choose our capital F of z to be log 0 of z minus 1, and then of course this is just normal integration. We have the primitive of the final point minus the primitive of the initial point, and then we just evaluate each individual log, and notice that we add 2 pi because we want it to be in the range of 0 to 2 pi, and we get our answer of pi times I on 2. So now we can move on to our final question, and this is going to be a bit of a long one, so just stick with me. You might have noticed this before. It's called a Dirichlet integral, and generally it's really hard to evaluate it in terms of real integrals, but it does become much more possible with the use of contour integration, which we'll see later. So they want us to integrate with a function which they give us, which is e to the I z over z, and they want us to integrate along a contour. Of course, they don't give us the contour, so we have to develop one ourselves. And the main thing that we want to know is that we want to integrate along the real axis, right? From minus infinity to infinity. But we can't have a contour with an infinite line in it. So generally what we do is a trick, which is essentially we have a line from 2 points minus r to r, and then what we do is we take the limit as r approaches infinity, and so we should get a line from minus infinity to infinity. Then we also have to take note that the line here passes through our 0, but of course it's not defined at 0 since it's e to the iz over z. So we can use something called indenting, and that's essentially we add a semicircle which goes around this point. And the reason we use a semicircle is because it's much easier to evaluate a semicircle than most other curves. And let's just call the radius of this semicircle epsilon. So we can take the limit as epsilon approaches 0, and that's what should get us our 0 right here. And that's just kind of a way we can cheat it. Then, of course, we want to use a closed contour. The main reason is because generally we'd like to apply something like Cauchy-Gaussat or Cauchy's residue theorem, which we'll learn later. So we have it closed up, and we use a semicircle or an arc to close it up because obviously arcs are very easy to evaluate compared to other curves. If we had something like this, I think you'd find it much harder to evaluate, even though it is a closed curve. And of course, we can name our contours individually. So we have the red semicircle, the larger one, being capital gamma, and the smaller one, the green one, being lowercase gamma. And we can just define lines by epsilon to r and minus r to minus epsilon. So of course we want to take the integrals as r approaches infinity and epsilon approaches 0 at the end. And of course we can use Cauchy-Gaussat theorem, which means the integral of the contour, since it's both closed and simple, but in this case we just need to know that it's closed, is equal to 0. And what we're going to do is we're going to use these last two integrals because we know that they range from epsilon to r, which is going to be 0 to infinity later, and we're going to transform them to become our sine x on x. So of course we want those to be in terms of x, so the first thing we do is we just have a dummy variable. So for this first integral, we just replace all z's with x's, and the reason this works is obviously because we are integrating with bounds, and so what that means is in the end, the integral is dependent on the bounds rather than the actual letter that we integrate with. Then we can look at the second integral, which we want to have the same bounds as the first, so we can combine. And so we want epsilon to r bounds. And the way we do that is we can have a u sub of z equals minus x. We take the derivative of both sides, and what we should get is dz is equal to minus dx, and our bounds for x become r to epsilon. So we sub everything here. We can cancel out the minuses, and so we should get this. But obviously we want r at the top since r is larger, so we take out a minus and flip the bounds. Then what we can do is we can evaluate our third and fourth integral. We'll start with our third. And so what we want to do is we want to parameterize it. So something to note is that in our contour right here, it is traversed anti-clockwise. So it'd be like this, this, and that. But obviously a flaw with that is that the inside semicircle is actually being traversed clockwise. So what we want to do is we want to take the reverse and then integrate it. So the reverse is a semicircle of radius epsilon, center 0, and it ranges from an angle of 0 to an angle of pi. So we have epsilon e to the iat. We can take the derivative, which has our I come down, and sub everything in. We can cancel these, and we should be able to factorize out this I right here. And what we get is I times this integral. And what we see is that if we take a limit as epsilon approaches 0, we get the power being equal to 0. So e to the 0 is just 1. And so we get this integral being equal to pi. So in the end, our third integral is equal to minus I times pi. Then we have our fourth integral. And so we know that it does traverse anti-clockwise, so we can just use normal parameterizations, and we get gamma is equal to r e to the it, since it is a semicircle with a radius of r and center 0, and of course an angle from 0 to pi. We can take the derivative as before, and then we can cancel. And what we can do is we can take the modulus. Of course, you've seen this before. Taking the modulus is a very common trick because it lets you evaluate integrals to be 0. And then we can just transform this into the modulus of this right here. And we don't use the ML lemma. The main reason is because it's kind of hard to see how this can be maximized since we have r approaching infinity at the end. So it's kind of unclear what we need to do. So instead we use a property that the modulus of an integral is less than or equal to the modulus of the functions and an integral overall. So what we can do is we can split up this e to the it to be cos t plus I sine t. And of course we can multiply it out and we would get 3 individual terms. The first one, I, is just a modulus of 1. The second one has r cos t, which we know is a real number. So obviously that is also a modulus of 1 since it's on the unit circle. And we'll get left with this term right here. So we want to find this term as it approaches r, as r approaches infinity. And we know that since sine is a real number, if r approaches infinity, this whole thing approaches minus infinity, so we get 0. And so the integral of 0 is 0, and what we see is that it's bounded, and of course by squeeze theorem, we can say that the fourth integral is equal to 0. So we can take the limits as r approaches infinity and epsilon approaches 0, and we can evaluate these two integrals. Then we are left with these two integrals So we get that these two integrals are equal to I times pi right here. And what we can do is, oops, these should be x since we've turned them into x's, but we can essentially just combine them. And what we see is that this top right here is very familiar since it's actually a different form of sine. So we know that sine x is equal to e to the ix minus e to the I minus e to the minus ix all over 2i. So in the end, we get that the top is equal to 2i sine x. And since 2i is a scalar, we can factorize that out, and we let that equal to our I pi. So our final step is, of course, dividing both sides by 2i. And what we should get is that our original integral is equal to 2 pi. So this is the end of our first part of the seminars. Please stay tuned for Thursday. These are recorded. These slides will be uploaded, and the next part is going to cover things like series and Fourier transform, Laplace transform, residues, and then the Cauchy integrals. So yeah, thank you for coming, and see you next time. Also, of course, thank you to Fred, who presented before me.